Hello again. In this video, we will explain the oxidation and reduction that occur in a chemical reaction or redox. The oxidation is a process where a substance forms a bond with an oxygen. For example, the sulfur here in this reaction is oxidized because it bonds with the dioxygen and forms the sulfur oxide. And the same for the hydrogen here in the formation of water. The hydrogen is oxidized because it bonds with oxygen and forms H2O or water. The reduction is the opposite. It's when a compound contains an oxygen and this oxygen is, so the bond is broken and the oxygen, for example, is exchanged with another element. For example, in this reaction, we have the iron oxide, which had already been oxidized. So now it's a compound that has the oxygen element. And in the presence of carbon, we get the formation of the CO2, carbon dioxide, and therefore the iron here is reduced because it no longer contains the oxygen. And now it's just solid iron, so the pure substance again. So the same for copper oxide. Here it has originally the oxygen element, and with the presence of the hydrogen we get the formation of H2O and the copper in its solid state again. So here we have a reduction, and here we have an oxidation because the element is bonding with O, oxygen. And here the element originally contains, so the compound originally contains an oxygen, and now the bond is broken, and that's why we get a reduction process. In the former two examples, the carbon here is called a reduction agent because it contributes to the reduction of iron oxide. And the same for hydrogen here is called a reduction agent because it contributes to the reduction of copper oxide. But it can also happen, so the reduction can happen without the presence of a reduction agent. So just by one single compound that contains an oxygen element and that decomposes by itself to form three different compounds, for example, like in this case, and all of them contain oxygen. That's true, but the thing is the number of oxygen in the beginning was 4 oxygen, and we had 2 of this molecule or moles. And now we have only 1, so here we have 4, and here we have 2, and here we have 2. So the total is still 8, but it's split between 3 different compounds, and therefore each of these compounds is reduced because the total number of oxygen was reduced. And this reaction happens just by heat without any reduction agents. However, oxidation and reduction not only occurs when an oxygen element is present, but also in the absence of oxygen. And it's defined by the loss or gain of electron. So, for example, let's take a look at this reaction here. So the sodium and the chlorine react together and form the sodium chlorine, which is an ion. And when it's just sodium by itself and chlorine by itself, then we have in the original state this electronic configuration. Sodium is right here, and you see this is the first, second, third period. So the electronic configuration of sodium ends with 3s1. And the electronic configuration of chlorine ends with also 3s2, of course, because here it's saturated, and p the p orbital contains 5 electrons. So 3s2p5 for the chlorine. Now, if we go from chlorine to Cl minus, it means what happens here? One of the electrons residing in the last orbitals of sodium is transferred from the orbital of sodium to the orbital of chlorine. By this, we get an excess electron for the chlorine, and that's why instead of p5 now we have p6. So we get a saturated orbital. And the same here, instead of 3s1 now we have 3s0, which means the 3s is not occupied anymore, and the electronic configuration would end with p6 here. So with 2s2p6, because the 3 is s0, 3s0. So as if it doesn't exist. In this case, we have from 1 to 0 means that the number of electrons for the sodium is reduced, but the charge is increased. Here the charge is neutral, so it's 0, and here the charge is +1. So just a moment to erase. Now, here we have instantly a charge of 0 for the sodium, and at the end of the reaction, the sodium has +1. Yes, the number of electrons is reduced, and that's why the charge increases, because you know that the charge is plus when we have more proton than electron. So in the end, we get +1. But when we have more electron than proton, in the end, we get -1 because the charge of an electron is negative. So from 0 to 1, the formal charge increases. And by this, we call this an oxidation. So the sodium was oxidized. When the charge is reduced, so we have a gain of electron, like in the case of chlorine, we have a gain of electron, but the charge is initially 0, and now it's -1, because we have more electron than proton. One excessive electron. So from 0 to -1, we have a decrease of formal charge, a reduction, so the formal charge is reduced, and we call this that the chlorine was reduced. So here we have a redox, a reduction at the same time happening with an oxidation through exchange of electrons between the sodium and the chlorine, so the oxidant and the reducing agent. Where the sodium is oxidized and the chlorine is reduced. And how do we know that? Just by looking at the charges, comparing them to the initial state. Now, let's review the first two examples where we had the oxygen. So if you want to apply this definition to a compound that contains oxygen, we can of course assume that since they are already bonding with an oxygen or losing an oxygen, then it's definitely either an oxidation or a reduction. But if we want to apply this same rule to see how the formal charge evolves, then we can also consider the charges of each element separately in the reagent and in the product. So we know that the more electronegative an element is, then it's more likely to capture an electron from its coexisting element in the same bond. Or, for example, get the delta plus and delta minus. The delta minus means that this element is more electronegative and it attracts the electrons that originally reside in the neighboring element. So they still belong to the other element, but they are closer to this electronegative element. We just explained previously what how electronegativity works. And if we want to take a look here, we have this example SO2, and if you remember, the electronegativity in the table increases from bottom to top and from left to right. And of course you can see also the charges. So if you compare S, sulfur, and oxygen, then oxygen is more electronegative than sulfur, which is, if you remember, we said that FON, F-O-N, are the most 3 electronegative in the periodic table. So this also definitely applies to sulfur, which means that sulfur is more electronegative than oxygen. So when we have a compound where there's an element that's normally not likely to become in cation, for example, in the SO2, like in the case of SO2, if you check the table again where we talked about which compounds become cations and which ones become anion, those elements were more likely to become cations here, including the metals in between. So if you check the table again in this chapter, then because it's easier to just lose 1 electron or 2 electron than to, for example, gain 4 or 5 electrons to become like a noble gas, so with saturated orbitals, if you remember this. So in the case of oxygen, the oxygen gains 2 electrons and becomes saturated, like a noble gas, like neon. So therefore it becomes O2 minus. But in the compound SO2, if one element is gaining electron, then the other element must definitely lose electrons. So the S, it belongs to the same group of oxygen, but it cannot at the same time as oxygen also gain 2 electrons to have a saturated orbital, although it's easier. But since in this case one element has to act as an anion and the other has to act as a cation, then the more electronegative element will be this anion, gaining the electrons. So if we take a look here again, then in this case, the oxygen becomes 2 times positively charged, so O2 minus. And by this, we can deduce the charge of the sulfur. So we have S and we have O2, right? And the oxygen has 2 minus, which means 2 minus times 2, because we have 2 oxygen elements in the sulfur oxide compound, gives us in total 4 minus. Therefore, in order for the SO2 to become neutral, the sulfur alone will be losing 4 electrons and getting this 4 plus charge inside the SO2. But after it's bonding with the oxygen, of course, the charge disappears because the total amount of electron did not change. It's just transferred from one element to the other, but in the same compound it's still neutral. The charge is 0 at the end. So let's apply this rule to see the formal charge, how it's evolving. We start from a 0. Let's do it in red. We start from a 0 on the S because it's neutral at the beginning, and it's just a normal state, and we start from 0 for the oxygen. At the end we have -2 for the oxygen, times 2 of course, plus 4 for the sulfur, which means from 0 to plus 4 we have an increase of charge. This means that the sulfur was oxidized, and this verifies what we explained at the beginning of this lesson when we said that any element gaining an oxygen is automatically oxidized. It's simply because, yeah, the oxygen bonding with any other element, it's more electronegative than the rest, and therefore it's the one that will be gaining the electron. And by this, the charge of the other element will definitely increase because it's losing its electron. So it will be oxidized. And the oxygen passing from 0 to -2, here we have a decrease of charges or a reduction of charges, and therefore the oxygen was reduced. If we apply the same thing to water, we start from 0, 0. Of course, oxygen, again, is more electronegative than hydrogen. 3.5, 2.2. So oxygen will become 2 times negatively charged, so -2. 0 to -2, it's a reduction. And H plus will become, of course, +1. We see H is here, so it's just lose 1 electron to have a saturated orbital, which is an orbital without any electrons inside, because the hydrogen originally has 1 electron only in its s orbital, and only 1 orbital, which is s, and when it loses this electron, it just becomes with an orbital without any electron, only a proton. And that's why sometimes we call H plus proton. So again, here we see that, so we have H2O, O has 2 minus, 2 times +1, the total is 0, which is verified that H will have only 1 plus. So from 0 to 1, the charge has increased, H is oxidized. And from 0 to -2, the charge is reduced, oxygen is reduced. We have a redox here happening where the oxygen undergoes a reduction and the hydrogen undergoes an oxidation. So this is just a repetition of what I just explained, how to quantify the oxidation state in a molecule, which is the oxidation numbers. The oxidation numbers are the charges that we mention on top of the element to say how many electrons this element has gained or has lost. And normally they are written in Roman numerals on top of the element. So like in this case we just did, the S was 0 and at the end it became +4. We write it in Roman letters, and the same for the oxygen. And therefore sulfur has changed its oxidation number from 0 to +4. So it was oxidized because the number of oxidation has increased. The oxygen changes oxidation number from 0 to -2. So the number was reduced, and therefore oxygen was reduced. And the same for the other, the reaction of water, which I just explained, where the hydrogen was oxidized and the oxygen was reduced. Now, these are general rules to consider when you want to write the oxidation numbers. First, you don't always have to write the electronic configuration and check which one is more electronegative to determine the oxidation numbers, because you can follow some simple rules. When you have an homogeneous bond, like for example O2, F2, S2, so a bond which is composed by only one type of element, of pure element, then the oxidation number is 0, of course, because there is no element more electronegative than the other, because all of them are similar. So that's definitely here, like in the case of dioxygen, both elements get 0. For the heterogeneous bond, which is most of the cases, you have the halides get -1. The halides are those that are like the chlorine, for example, and the fluorine that are here in this group. So right in front of the noble gases, right before the noble gases. So group number 7. These are the halides, and they get normally -1 charge because, yeah, it's just one gaining of electron, and then they get a fully saturated orbital. So it's very easy for them to just gain one electron from the neighboring element. So halides get -1. Then you have the oxygen always gets -2 if you start from a neutral oxygen, but if you start from an oxygen which has already was carrying a negative charge, then you get -1. Yeah, because you start from O-, for example, and at the end you get O2-, so it's -1 difference. Then you have the hydrogen and the alkaline metals. They get all +1, like the ones that belong to the first group. These one here, they got +1. They get +1, all of them. Sodium, lithium, hydrogen, and so on. Then you have the alkaline earth metals, the one that belong to the second group, like beryllium and magnesium. They get 2+. And you have other metals that get between +1 to +7 mostly, and which we talked about before, that we could determine from the number of electron lost or gained, the number of electron gained compared to their anion, for example. If you remember, we talked about iron, we talked about Au, we can have Au plus or Au2 plus or Au3 plus, and the one to know which one here we are talking about, if it's gold 1, gold 2, gold 3, then you have to check with which element it's bonding. So if it's with oxygen to minus, then it's more likely to have, for example, if it's AuO, then it's gold 2. But if it's Au2O, so then it should be gold 1. Because in this case, you will have a total of 2+ here. 2 times 1 is 2+, and 2-. The total must always be 0. So that's why for the metals, the other metals that reside between the second and the third group, you can have different number of oxidation numbers. But the rule is that the sum of oxidation number in the same compound at the end must be equal to 0. Let's apply what we learned to a real-life example, which is the electrochemical cells, or in other words, the battery. So here in this reaction, we start from a zinc metal and a copper sulfate solution. The zinc metal is, of course, a solid in its natural state, so the charge is 0. And the copper sulfate, we have to figure out the charge of each element separately. So we have copper, sulfur, and oxygen in one compound. We know that the oxygen is 2-. This is among the rules that we just learned. So -2. And the copper is normally 2+ or 1+. How do we know? We determine depending on the charge that we get from the sulfur. So in total now we have -2 times 4 for the oxygen, which is -8. So the copper and sulfur both together should have a +8. Now for the sulfur, we see where in the periodic tables it's located. So it's right here in the 6th group. So in order to have a saturated orbital, it can either gain 2 electrons, which is not the case because we already have 8 minus and we want to balance this out, and the copper cannot get 8 plus, for example. So definitely the sulfur here should become positive. So is the one to lose electrons. So the sulfur, to become like a noble gas, it should not gain 2 electrons in this case, but lose 1, 2, 3, 4, 5, 6. So it becomes, until it becomes like the neon. So sulfur is 6 plus. And therefore the copper should have 2 plus here. So it's copper 2. Because we also have copper type 1, which is Cu plus, because this belongs to the metals, which can have different oxidation numbers. Alright, so the total is 0 again. And now for the copper here, because it's a solid, then it should be 0. And if we repeat the same thing here, then we should get -8 for the oxygen, +6 for the sulfur, and +2 for the zinc. This is also an easier example here because the zinc is known to have 2 plus normally. So now let's determine the oxidation and reduction. So here it's clear that the zinc got oxidized because from 0 to +2 it lost electrons, but the charge has increased. And the copper, from +2 to 0, the charge was reduced, so the copper is reduced. And we have a kind of exchange of electrons from zinc to the copper. And since we have kind of a metal and a solution, liquid solution, then in this case we have a flow of electron, and this is how a battery functions. But to be more specific, we can divide this reaction into 2 different reactions by just dropping the sulfate and just showing the oxidizing agent and the reducing agent into the 2 clear oxidation and reduction reactions. So we write them like this. The zinc here, the zinc got from 0 to +2, which means it gave away 2 electrons. So the zinc, from zinc solid to zinc aqueous in water, it gives 2 electrons and becomes Zn2+. The copper is originally Cu2+, so it starts as a solution in water, and it receives the 2 electrons that the zinc gave, and it gives us the copper solid. So this is the oxidation reaction, because we know that it comes from 0 to +2 has increased, the oxidation number has increased, and the oxidation number here was reduced, so this is the from +2 to 0. So this is the reduction reaction. But how do we know the flow of the electron and how much it will circulate? Because at some point the battery will just die and no flow will happen anymore. So how do we find out from if the flow of electron is like this or like this? So in this electrochemical cell, we have negative terminal, which we don't know which one, and a positive terminal. The negative terminal is a metal that gives away the electron into the solution. We have a solution here with water inside. This or this, so we don't know yet. The metal terminal, which is negative, will give away electrons in the solution, which contains ions, and these ions will capture the electrons released by the initial metal terminal, which is the negative terminal, and will deposit on the positive terminal, regardless whether this one or this one. So we will determine later on which one is the negative, which one is the positive. So let's suppose zinc is the negative terminal. Then in this case, zinc will be giving away the electrons in the solution, which means this metal is decomposing, and it will, so instead of be that thick, it will be, for example, this much thick, because part of it is decomposed in the solution, giving away some electrons in the solution, which is here in water, where we have copper ions. And of course, it's giving away zinc ions. So the zinc ions in the solution are increasing, and the copper ions are capturing the electrons released by this metal, forming copper metal solid. So this metal is depositing here on this copper metal, and therefore the thickness here is increasing. If this is the negative terminal and this is the positive terminal, which we will determine right now. So if the flow of the electron goes from zinc to copper like this, then what I just explained is true. If it's the opposite, so if it circulates from copper to zinc, which means the copper is the negative, for example, like this, then it's the opposite. This one will reduce its thickness because it will decompose, and this one will thicker and thicker because more zinc metal will deposit here, because the copper will give away the electrons in the solution. The copper ions in the solution will increase, the zinc ion will decrease. They capture the electron, they deposit on the zinc metal, if this is the negative one, which we will find out right now. So to determine the flow of electrons in a photochemical cell, we have to check the voltage or the standard electron potential. And this is just verified or classified depending on which metal is in the solution, which anion is used. So if we are talking about zinc and copper, because we can have electrochemical cells from different elements as well, but if we have zinc and copper, then the voltage here of the zinc is minus 0.7 and of the copper is plus 0.33. So we put the higher voltage on top, the higher potential on top, which is the copper here. So the copper here, this is the reaction, of course, plus 2 electrons. The copper ion will capture 2 electrons and will give us the copper solid metal. The one on the bottom will be this one with the lower potential, which is the zinc ion, will capture 2 electrons and will give us the zinc solid. The flow will be clockwise like this. So like this. Because this is the higher potential, it's placed on top, and this is the lower potential, it's placed on the bottom. And to determine the circulation, the flow circulation direction, then we just determine it clockwise like this, and therefore it circulates like this. So the reaction here happens in the opposite way. So the zinc metal is actually like this, decomposed into zinc ion and electron. So the starting point is the zinc metal and not the copper metal, because the copper is actually reduced from 2 plus to 0. The zinc is oxidized from 0 to 2 plus. So the starting point is the zinc. And we said that this is the flow, which means the copper ion is the one that's capturing the electrons and depositing on the copper metal. So if we go back to our cell here, the copper ion is receiving the electrons and depositing on the copper metal, which is the positive terminal, because it's receiving the electrons, and the one that is giving the electrons and that is being reducing. So it's becoming like this until it's totally consumed, is the negative terminal, and it's called the anode. And this one is called the cathode. So the cathode is the one where a reduction takes place. We said that the copper is going through a reduction because the charge is going from +2 to 0. So this is called the cathode, and it's the positive terminal of the battery. And the anode is where the oxidation is taking place. So it's the zinc giving away 2 electrons and giving zinc ions in the solution. So we have an increase of zinc ions and we have an increase of copper metal, and the flow is from the minus to the plus. It's actually going from the minus terminal to the solution, and from the solution to the copper metal. Now, if we want to calculate the voltage of a battery, there is actually a complex formula which we will not go into its math, but we will just explain it briefly. So we have, of course, we said that each of the reducing and oxidizing agents have some kind of voltage. So their standard potential, which was in the table. For the copper, it's 0.3 volt, and for the zinc, it's minus 0.7 volt. And we are going to use them in the Nernst equation. There is a constant called R, which we just replace in the formula. There's a temperature constant, which is 298 Kelvin, and there's a modest 2.3 just to convert from ln to logarithm. So we just multiply by 2.3 and we get logarithm. Because the potential of something, which is the P operator, which we talked about in the first lesson in the acids and bases, is minus log. So we deal with minus log concentration something. So we deal with the logarithm function, And we have also the Faraday constant, which is equal to 96,000. And if we replace everything here, we have 8.3 for each of the copper and each of the zinc. 8.3 times 298 divided by F, which is 96,000, times 2.3 to convert to log function. We get 0.059 volts, and the Z remains the same at the bottom. And we start from the E0, which is the nominal voltage or the standard potential of the element used. For example, for the copper, it's 0.3 plus 0.059 volt divided by Z, logarithm of concentration of the oxidant to the concentration of the reducing agent. The oxidant here in this case is the cation, of course, because this is going through a reduction, so the oxidant is being reduced. The oxidant. And so we have this equation at the end. And for the zinc, the same thing here, but the E0 is minus 0.7 from the table. We calculate the same numbers, we get 0.059 divided by Z, log concentration of the oxidant, which is in this reaction, should be like this, of course, because we start from the zinc metal and we get at the end the zinc ion. So the oxidant, this is an oxidation reaction, so the zinc is being oxidized, which means that this is the reducing agent and this is the oxidant again. So concentration of zinc ion to zinc metal. Next, if we consider that the zinc, any solid, has a concentration of 1, just like we explained in the previous lesson of acids and bases and the one before as well. So yeah, the solid has always a concentration of 1 if we have some aqueous reaction, because it does not interfere in the reaction itself. So it's just a solid. It doesn't take part of the liquid, so it doesn't have some quantity dissolved in the liquid. That's why we consider it's 1. It's a solid. And if we want to calculate the voltage of the battery, then we have to calculate the difference of potential between the positive terminal and the negative terminal, right? This is how we calculate the voltage. So we just do E1 minus E2. E1 is this, 0.3 plus all this, minus 0.7, which is plus 0.7 volts, plus all this. Now, if we pretend that the concentration of the copper ion in the solution, in this solution, and of the zinc ion is equal to 1 mole per liter, equal zinc equal 1 mole per liter. This does not apply to all cases. We just take one particular example. If the concentration of these ions is equal to 1 mole per liter, Then if we do the sum, we get logarithm of 1, the concentration here is 1, is of course 0. Logarithm of 1 is 0. So all this is 0. So we get this is 0 and this is 0. We get plus 0.7 plus 0.3, which is equal to 1 volt. So when we have a battery or electrochemical cell with 1 volt, it means the concentration of the ions in the solution is equal to 1 mole per liter. If we have another concentration, then the voltage, of course, will vary at the end, and this will be determined depending on Z. So we should have other given data in the exercise, for example, to calculate this. Now this can be used also not only for to produce a flow of electron and produce, for example, electrochemical cells, but also to protect from corrosion. Corrosion is the effect of a redox reaction taking place, where the iron, for example, is oxidized. And this happens when we have two different metals, one acting as a reducing agent and one acting as the oxidant. Like in the case of, for example, copper and iron, if we have some surface that has to function on water, like for example a ship hull, and in the presence of water, the copper is normally the iron is oxidized and the copper is reduced. So in the presence of water, because all around there is the water solution, the iron will give away. First, to determine the flow, we check the table again, this one, and we see iron is not mentioned in this table, but it's given here in this example. So it's minus 0.04 as the potential, standard potential of iron, and it's plus 0.3 in the table for the copper ion. So obviously the copper will go on top and the flow will be like this. So this is the starting reaction. From the iron solid will give 3 electrons in water, and we will get an increase of iron ions, which means this iron is going through an oxidation from 0 to plus 3. And this copper is receiving those electrons, so 2 of them for every copper. And we have a deposit of copper metal. And we have a corrosion effect because this iron is being oxidized and losing its electrons. So to prevent this, we put some zinc patches which have an even lower potential, standard potential, where we will have now, at the beginning, the iron was acting like an anode or the negative terminal, and in the presence of zinc, now it will act as the cathode or the positive terminal and will go through a reduction from 3 plus to 0. If we place it on top, then the flow is like this, meaning that the zinc in the presence of water will give away 2 electrons and the zinc ion will increase. The zinc is being consumed. These electrons are captured again by the iron ions which were released by the iron metal here in the water, and we have a deposit of iron solid again on top of the initial iron solid. So it's kind of decomposed, and then again it's reformed into solid due to the presence of zinc, which has a lower standard potential. And here, like this, the corrosion is prevented. So you can see that this oxidation and reduction, the redox that happens in chemical reactions, have so many applications. And in this lesson, we just learned two of them, which is how we can take advantage of the flow of electron to form electrochemical cells like batteries, and we can prevent corrosion.